Okay, ladies and gentlemen, I want to go over some problems that we talked about of the recent topics, most specifically some basic problems, again, some extra problems with capacitors, and then after those, some of the intro problems into finding equivalent resistance and currents in both basic circuits and decomposing networks of resistors in series and parallel. So that's the goal for this video, is again to give you detailed problem solving solutions as to what you can expect for things like homeworks, quizzes, exams, et cetera, et cetera. So let's jump right in. I'll take this over to my screen now. Okay, and these are three problems that we're going to do in capacitance, and I'm just going to clear some space here because all of this was worked out in class a couple days ago, so I'll just get rid of it. That way we can reproduce it and make sure that we're all on the same page. So no point in even erasing the first one. If we take a look at a 1.2 nanofarad parallel plate capacitor has an air gap between its plates. Its capacitance increases by 3 nanofarads when the gap is filled by a dielectric. What is a dielectric constant of that dielectric? We know the relationship between, if we have a capacitor and we fill it with some dielectric, we know how that relationship goes. The new dielectric, the new capacitance that you get is just equal to the old capacitance, the initial capacitance without the dielectric in there or with just air in there, multiplied by the dielectric constant. Here we want to find that dielectric constant, but they tell us the initial capacitance is 1.2 nanofarads. Then we got to be careful. They give us another capacitance here, which is 3 nanofarads, which is not the final capacitance, because as this problem is stated, it says that the capacitance increases by 3 nanofarads. So the final capacitance then has to be 4.2 nanofarads, namely 3 plus the 1.2. If we have the C initial and we have the C final, then this is really just a straight plug and chug. We can just divide both sides by C initial and solve this for the dielectric constant kappa, CF over CI, which comes out to be 3.5. A couple people asked me, what are the units of the dielectric constant? Remember, dielectric constant, not going to have any units. It's just a constant, right? And you can see that by the definition there, right? If apples has to equal apples and you have capacitance on one side and something times capacitance on this side, that something can't carry units, or else you'd have apples is equal to bananas or something like this, and it just wouldn't work out. Okay, the next one. 47 is a 25 picofarad parallel plate capacitor with an air gap between the plates is connected to a 100-volt battery. Okay, so again, we have an initial case. We know the initial capacitance, we know the voltage. A Teflon slab is then inserted between the plates and completely fills the gap. Well, if we put a Teflon slab in there, we're putting a dielectric, we're definitely going to change the capacitance. So unlike the last video on capacitors where we had a capacitor that we changed the battery, which meant the capacitor stayed the same, this one we're changing the capacitor by putting the dielectric constant in there. Okay, when that happens, but we keep that same 100-volt battery, what is the change in charge on the positive plate? So again, really then, if we have a capacitor, we know by definition it's going to be charge over the voltage. We know that the relationship between the air capacitor and the Teflon capacitor is that the new capacitor with Teflon will be equal to the kappa of Teflon times the original capacitance. And each one of them, if it's connected to a 100-volt battery, each one of them is going to have a different charge. Here they ask us for the net change in the charge, so not just the final charge, but the net change in charge. Let's put all that into practice, okay? So for number 47, okay, what do we have? We have a C initial is the 25 picofarads, and we have a V initial is equal to 100 volts. Okay, we know from the definition of capacitance, which is a ratio of charge to voltage, right? If we put a check mark next to what we know and underline what we don't, this is enough information for us to solve. And just to be clear here, these are all initials, yes? This is enough information for us to solve for Q initial. Q initial would just be C initial, V initial, which using these numbers gives us a 2.5, let me make that a little bit cleaner, gives us a 2.5 nanocoulomb initial charge, okay? That's the initial charge, but now what do we know? We then shove Teflon in there. Teflon, you can look up in your textbook, has a dielectric constant K of exactly 2. So we know then when we put Teflon in, we're going to change the capacitance of the system to be like the equation that we just used for the last one. Okay, and so from this, we then know also that C final is also going to be Q final over V final. But remember, V final is equal to V initial because we kept the 100-volt battery attached to this the entire time. Let's backtrack it now then. What do we see then? We see that if this is the case, we already knew CI and we knew kappa, so that means we now know C final. If we know C final and we know V final, we can now solve for Q final. So Q final is just C final, V final, which I get to be 5 times 10 to the minus 9 coulombs, or 5 nanocoulombs. If that's the final charge and we know the initial charge, we have clearly doubled the initial charge. So therefore, just to be clear as to what the problem is asking, it wanted not just the final charge, but it wanted the net change in charge. So that's the final charge minus the initial charge, which again happens to come out to be the same as what we had there, 10 to the minus 9 coulombs, or 2.5 nanocoulombs. However you want to give me the answer is fine. But again, when you're putting this into your homework system, you got to make sure that those numbers match, okay? So yeah, again, very similar to the problem that we did in the last video, except in the last video, we didn't change the capacitor. We didn't slide anything in there, right? We changed the battery. Here we kept the battery, changed the capacitor. The same story goes, and I don't want to belabor this point for the last one here. Let's just read it together. Parallel plate capacitor is connected to a battery and stores 4.4 nanocoulombs of charge. Then while the battery remains connected, same battery, sheet of Teflon, same material as before, is inserted between the plates. Does the capacitor's charge increase or decrease? Well, the dielectric constant of Teflon is 2. And so if C final is equal to 2 times C initial, it definitely increases. Well, how much does the capacitance actually increase? It doubles the capacitance, right? Because you're multiplying by a kappa, which is 2. By how much does the charge change? We just did this problem in 47. In problem 47, we've seen that the way that the charge changed, that we started from an initial of 2.5 nanocoulombs and went to 5 nanocoulombs, namely it doubled, which should make sense to you, just like how the capacitance doubled, the charge doubled. And so if that's the case, and we start with 4.4 nanocoulombs of charge, then the charge goes up to an 8.8 nanocoulombs, or another way of saying that is that it changes by 4.4. It doubles. Same problem in disguise. Okay, I'm going to pause this real quick while I bring up the problems on basic circuits and resistors. That way we have more practice on that. So stay tuned momentarily. Okay, so this is the first basic circuit problem that I want to work on that also highlights combining resistors in a certain way. So let's just talk it through. We have a battery, an 18-volt battery, connected to this sequence of resistors. What does that sequence of resistors look like? Well, it has 2 branches. One branch that has the resistor R1 and R2 in series with one another, and the other branch is just consists of the resistor R3. So the first thing that we should do if we want to find the total resistance is for us to talk this out. What do we see happening? When we go from the battery and we get to the point B, right, we have a junction right away, which right away the word junction or a split implies 2 things. It implies that something is in parallel, but it also implies that whatever the current that flowed in there has got to be the same as the current that flowed out. Let's hold off on the current until the next part of the problem. Let's only focus on the resistors for now and finding that total resistance. Okay, so again, we get to point B and right away we see a junction. We have a choice as to where to go, which means that those 2 branches are in parallel with one another. So let's spell it out. I see that R1 and R2, however, are in series. They're back to back, right? Which means that this combination of R1 and R2 could have been replaced with a single resistor that I'll call R12, such that R12, according to our resistor rules, that in series we just add the 2 resistances, which is going to be a 1 plus 2 or a 3 ohm resistor. So instead of having a 1 and a 2 in series, we could have just had a single 3 and it would have done the same job. Now, that what we just call that R12, although that combination on the top branch was in series with one another, that new combination, or that combination R12, that is the thing that is in parallel with R3. It's not just R1 that's in parallel with R3, not just R2 that's in parallel with R3, but it's the combination of R1 and 2 that's in combination, that is in parallel with R3. So the way that we're going to decompose that is that we're going to say this combination, which is now left over, which consists of R12 on the top and R3 on the bottom, we want to replace with one other resistor, which I'm now going to call R total, because we're out of resistors at that point, right? It's the total resistance. And using our formula for resistors in parallel, this is 1 over that total resistance is 1 over the first one plus 1 over the second one, which we need to be a little bit careful now with our algebra, right? This is a 1 over 3 plus a 1 over 6, and I'm leaving off the units for simplicity. 1 over 3 plus 1 over 6 means we have to get a common denominator, multiply the 1 over 3 by 2 over 2, and what we get is that 1 over RT is going to be 2/6 plus 3/6, which is also known as, oh gosh, I lied, 2/6 plus 1/6, which is also known as 3/6 or 1/2. So remember though, this is a place of contention, right? That it's 1 over RT is equal to 1/2, so therefore we're not done yet with RT. RT itself then has got to be 1 over 1/2, which is 2. So now we have the total resistance, right? And so now if we boiled this system down to a resistor that really looks like this, do we all agree our circuit now looks as simple as could possibly be, where we still have that same voltage, and now we just have this total resistor R sub T of 2 ohms. Okay, so we have found the first part. Now we want to find the total current. Well, remember, the beautiful thing here is that Ohm's law is true for any part of the circuit, including the entire circuit itself, right? So let me remind you what Ohm's law is. Ohm's law says that anywhere you'd like, right, the potential that you pay is equal to I times the value of that resistor. So if we're thinking of resistors as shops, stores, restaurants, right? I is the amount of people that go into them. R is the price that that store charges. Therefore, V is the net that you wind up paying. Okay, so if that's the case, then for the whole circuit, V total has got to be I total R total. We just said it's only one battery, so we know V total 18. We know R total is 2 ohms, so from that now we can figure out I total is 9 amps. Okay. So if there's 9 amps, then what that means is that here's I total, right? It's what leaves the battery. 9 amps leaves the battery, okay? And so now we have I total, but we want to find I1, I2, and I3, the current that goes through each individual resistor. Well, how does that go? So we picture ourselves as electrons, or you know, whatever we want to call ourselves, and we're leaving our dorm room, aka the battery. We make a right, we make another right, and we get down to point B, or what I've labeled as point B. At point B, we have a choice. Some people in our group are going to go up, and so we'll call that current I up. Some people in green will go down. We'll call that current in green ID for I down, right? We know these are friendly stores or friendly parties, whatever you want to call them, right? That after the people that go up, what do they have to do? They have to go through the store R2, and they have to go through the store at R1. The people who go down only have to go to the store at R3, but either way, when they're done with their journey, they both come back to A because charge is neither created nor destroyed. Namely, these are friendly stores. Everybody in Ohmstown gets back home to their dorm room safely to go party another night. So if that's the case, then we are ready to rock and roll and figure out these last two currents. How are we going to do that? Again, we use Ohm's law for each and every piece along the way. So the potential up has got to be equal to the current up times R up, By the same token, V down has got to be I down, R down. Again, if I'm using up and down as a notation for the people who went up and the people who went down. Now, when I say potential up, what am I merely saying? What's the potential difference in the up branch? The potential difference in the up branch, ladies and gentlemen, oops, started here and ends here. Namely, the potential difference in the up branch is still the same as the potential difference between points A and V. But ladies and gentlemen, V in the down branch is also the same as A and B because again, whether you go up or down, you still get to the same place. And remember how potential works? It works on distance or overall, so you can get an overall displacement. And therefore, if V up is the same as V down, what V is that going to be? And so all these V's are the same. There's only one. How much money, right, did people leave their dorm rooms with? They started at that dorm room with 18 volts. So they haven't spent anything yet. That will change in the next problem. They haven't spent anything yet. So V up when they get there or when they get to the junction at B, the people who go up still had 18 bucks in their pocket. The people who go down still had 18 bucks in their pocket. If that's the case, we now know V up is 18. We know V down is 18. We know what R up is. Let me remind you, R up was the net resistance for the top branch, which was not just R1, not just R2, but what we called R12, which we already have a value for, which is 3 ohms. We already know down it's one and only one resistor, that's our 6 ohm resistor. So we also know R down. If that's the case, we can now solve these for I up and I down. Solving that for I up, we see that I up is V up divided by R up, which V up is our 18 volts over 3 ohms, which knocking that out gives us a 6 amp current that goes up. I down is going to be V down over R down, which is our 18 volts divided by 6 ohms, which is 3 amps. And what do you know? If 6 went up and 3 went down, how much went in? We said 9 went in. And we know that whatever comes in has to come out. That's our gut check. That 9 came in, and what flows out is 6 plus 3. 6 goes up, 3 goes down. The big key takeaway here that I think a lot of people are prone to forget, right, really comes, in this piece, this piece here that I'm putting in green. Okay, it kind of looks like a weird animal shape. Why is this the piece? Is because, again, a lot of people will forget that it's not the current that's the same. We can't just say that, well, 9 went in, so 4.5 goes up and 4.5 goes down. That's not what we can say because we don't know that to be true. What we do know to be true is that between those 2 points, namely whether you go up or whether you go down, you only traverse from A to B in either path, and you can only take one path. So everybody that got to point B started with 18 bucks in their pocket, whether you went up or down. So therefore, the potential difference across B to A is the thing that in a parallel or in a junction has to be the same. That's what we talked about in the last video about circuits, but that was a bit abstract. Now we're actually seeing it come into play here. I want to do one more. That way we have another one fully worked out with very similar, small circuit, but similar scenario, but with things just ever so slightly tweaked. That way we can be sure that we see how more of this will make sense. Okay, so I want to do this circuit now, which is very similar. We have a battery attached to, again, 3 resistors, and that should be R1 right there. Okay, but the configuration of the resistors this time is quite different. This time, if we think about it, what happens? We leave our dorm room, namely the battery, and we all go out, and what happens? We all don't get a choice. We all have to go through R1 first. After we go through R1, then we get a choice. Do we go up to R2 or do we go down to R3? So in order to make this a little bit easier when we get down into the nuts and bolts, I'm going to put 3 points on this, point A, point B, and point C, which are those red circles marked there on the map. All the voltages are given, all the resistances are given, and I want to find the exact same things that we did before, which are as follows. RT, IT, I1, I2, I3, namely total resistance, total current, current goes through I1, current that goes through I2, current that goes through I3. So to find the total resistance, we're only focusing on the network of resistors. If that's the case, then we have to talk it through. What do we see? We see R1 is in series with something, but what is it in series with? Well, R2 is definitely in parallel with something. Hopefully, the first thing that we identify here is that this combination of R2 and R3, we can replace by some new resistor that we'll call R23, right? A single resistor, because the two of them are in parallel. So this is just going to be 1 over R2 plus 1 over R3. Okay, again, using the values that we have, this is a 1 over 6 plus 1 over 3, and those numbers were conveniently chosen so that R23 matches the math that we did last time, which is going to be 2 ohms. Now, that combination of R23 is what's in series with R1. So we have now reduced the network of resistors to this, which we know we can replace by a single resistance that I'll call R total because it has satiated the rest, which is R total is R1 plus R23, which is going to be, oh, R1 is 4, I apologize. 4 ohms plus 2 ohms, namely a net total of 6 ohms. So we could have replaced this combination of R1 in series with R2 and R3, which are in parallel with each other. Instead of that combination, we could have replaced it by one single 6 ohm resistor. Okay. Just like before, though, what we have now done is we have now simplified the circuit to be the total voltage, a total resistor, which means therefore we can figure out the total current which comes out. Again, we apply Mr. Ohm, he owns the town, right? He sets all the regulations, right? His law holds in every establishment, therefore it holds for the entire town. That tells us then that I total will be V total over R total, which again now is going to be our 18 volts, but now divided by 6 ohms, and this is going to be a total of 3 amps. So when we leave up here, 3 amps is what leaves the battery. Okay, so if 3 amps leaves the battery in current, now we're in a position to figure out all the rest of these. Well, how do we know what current goes through I1? Well, we all said that if we all leave our dorm from the battery and we all are going this route and all the parties or all the restaurants are safe, then what do we know? Once we leave the battery, here we go, we bang the right, we bang another right. Well, there's no choice. We all have to go through R1. Well, how many of us are there? There's 3 amps of us. So how many of us have to go through R1? All of us. And we all get out, right? We can't be created nor destroyed. It's a safe party. So if 3 amps goes in, 3 amps comes out. Namely, yes, the value for the total of the current was 3 amps, but that's also how much goes through I1. Because again, if we started with that much has to flow through I1 because you don't get a choice. What do we have to do though for going through R1? We still, Mr. Ohm sets the laws here, right? So although we didn't lose any people, right? That's why we still have 3 amps. We still have to pay a price, right? We started with 18 bucks in our pocket when we left the dorm, but we still did something. We went to one of the stores. We went to the store at R1. So how much do we actually pay? Do we pay all 18? Well, if we paid all 18, then we wouldn't be able to go through that parallel branch of R2 or R3. So how much do we pay? Well, this is why it was important for me to put the points A, B, and C on there, right? Because again, if we're talking about potential and potential difference, then hopefully we see that the potential difference between points C and B, right, how much do you pay to go from C to B? Well, you pay, according to Ohm's rules in this town, whatever you did in that segment. And what you do in that segment? You went across that store, that resistor, and how many of you went? I1 of you went. Well, we know what I1 is, it's 3 amps, and we know what R1 is, it's 4 volts. This is 12 volts. So how much did it cost you? How much did it cost you to go this leg of the trip? It cost you, oops, it cost you 12 volts to go this leg of the trip. Okay? So if it costs you 12 volts to go that leg of the trip and we started with 18 volts, right away then that tells us that we only have 6 volts left to go the rest of the trip, which is the potential between B and A. Now, the potential between B and A, however, is right back where we were in the previous problem. These are two things in parallel. So what happens? Some of us go up, some of us go down. We'll use the same notation as before, I up and I down. We can't split it in half because we don't know if that's true. But the only thing that we do know that is true, which again, I'll spell it out like we had before, is that V up has to be the same as V down because it's just the potential difference between A and B. And we just said, if we spent 12 to go from C to B and we started with 18, we know then that we only have 6 ohms left, which means we know V up and V down. But again, Mr. Ohm sets the laws. So these have to be true. Put a check mark next to what I know and underline what I don't, because R up is just the resistor that we called R2. R down is the resistor that's on the bottom branch, R3. And so from this, what can we figure out? This tells us right away then that I in the up branch is 6 ohms over the resistance in the up branch, which I have to remind myself what that is, 6. Oh, I'm sorry. This is supposed to be volts in the numerator, amps in the denominator. Gosh, not amps in the denominator, ohms in the denominator. And what do we get? 1 amp goes up. I down is going to be V up divided, I'm sorry, V down divided by R down, which is 6 volts divided by 3 ohms, which is 2 amps. And what do you know? The two currents that we get, 1 amp plus 2 amps is equal to 3 amps. Another way of saying that is, yeah, I up plus I down had to be the same as what went in, which was I1, which we also know as I total. So we have all of the currents, which is everything that we wanted. So really need people to focus on this because we're going to play this game over and over again for like a good week, week and a half. Okay. The only thing we're going to do is make the circuits more and more complicated, add more resistors, add different combinations of them, right? Like a parallel branch with a sub-parallel branch in them. And add more batteries, give you more money to play with as you travel around Ohm's town. But everything that we just did here, it's all going to be exactly the same. We're going to be applying the junction rule. Whatever flows in has to flow out. And then across any potential difference, we have to analyze Ohm's law. If we can grasp those piece by piece, we'll see that none of this is just an interesting exercise in kind of piecing it all together and puzzle solving. I think they're really fun. But as you can see, these first two simple examples give you enough to chew on and enough really to take the jargon and the theory from the last two videos and hopefully put them into practice. Okay, ladies and gentlemen, the next videos will go into more of using those basic circuit rules, more complicated circuits, and then a whole lot more problem solving within this material. So I hope that you find this helpful for not only this week's homework, but for just doing all these problems in general. And I look forward to seeing you all again next week. Have a safe and happy weekend.